Okay, engineers, on this video we are going to see the Laplace transform of integrals. I have to remind you what is the Laplace transform of the derivative. The Laplace transform of the derivative generates an s times the function, sorry, this is capital F because I have f of t, f of s minus f of 0. Now, is s times f of s. Now, if you happen to have the second derivative, then it's going to be s squared f of s. So for every derivative, you have a multiplication of s. Okay, now, what will happen if instead of having the derivative, you have the integral? And you have to remember that the integral is the opposite operation of the derivative. Okay, so what will be the opposite operation of the multiplication times s? Well, obviously, it is the division. So we assume that the Laplace transform of the derivative will be f of s divided by s because it is opposite. Okay, let's see if that is actually true. Okay, let's do the Laplace transform of the integral from 0 to t f of tau differential of tau. We can actually have f of t differential of t is exactly the same. It doesn't change anything. Okay, now, because we don't know what is the Laplace transform, we are going to use the definition. The definition of the Laplace transform is the integral from 0 to the infinite exponential minus st, and then the integral from 0 to t f of tau differential of tau, and then here differential of t. Okay, as you can see here, we will have two integrals inside. Okay, but the differential is different. That is why we write it like tau and differential of tau in order to differentiate from the differential of t here. Okay, so what we are going to do is an integration by parts. So how are we going to use integration by parts? We have to write like this. Integral from 0 to infinite, integral from 0 to t f of tau differential of tau, and then exponential minus st differential of t. For the integration by parts, we are going to use this as u and this as dv. So u is the integral from 0 to t f of t differential of t. So the differential of u is the integral cancels, so it's going to be f of t differential of t. Okay, so this is tau, this is differential of tau. Okay, now originally what you have to do here is derivative of u respect to the time, and the result is just f of t because it's the opposite operation, but we need the differential, so we pass the differential at the end as a multiplication. Now, differential of v is equal to the exponential minus st differential of t. We have to take the integrals, then here minus s, minus 1 over s to compensate. So v, the integrals, is going to be minus 1 over s exponential minus st. Now let's apply the integration by parts. This is going to be u times v, integral from 0 to t f of tau differential of tau, and then times minus 1 over s exponential minus st from 0 to infinite, and then minus the integral of v differential of u minus 1 over s exponential minus st differential of u f of t differential of t from 0 to infinite. Okay, so this is just the integration by parts. Okay, so let's continue here. Now we have to do the upper limit minus the lower limit. Okay, so it's going to be here, it's going to be integral from 0 to infinite because you replace the value of infinite here, f of tau differential of tau, and then minus this minus outside over s exponential minus infinite. So that is the upper limit. Minus, well, plus minus this times this minus, the lower limit, integral from 0 to 0 f of tau differential of tau, and then over s exponential of 0. Okay, be careful here, and then plus this part, 1 over s integral from 0 to infinite exponential minus st f of t differential of t. Sorry for the space, but I want to focus on this part because exponential minus infinite, it happens to be 0. 0 times anything, this integral is very ugly, but we don't care about the value of this integral because times 0 is going to be 0. So all of this is 0. Okay, now exponential of 0 is 1, but how much is the integral from 0 to 0? The integral from 0 to 0, I don't care how is f of tau, it is always 0, because if you remember the integral from a to a, so you don't have the integral from a to a of f of x differential of x, because you go from a to a, then there is no area, so it is equal to 0. Okay, so that is why this is 0. So in engineers, in the end, all this part is just 0. So what is left? Okay, just remember from where we come from. We have the Laplace transform of the integral from 0 to t f of tau differential of tau, and that is equal to only, this is 0, the only thing left is this part, 1 over s integral from 0 to infinite exponential minus st f of t differential of t differential of t. Now, have you seen this before? This part? Well, that is actually the Laplace transform definition. The Laplace transform of what? Of f of t. So in the end, this is just 1 over s, the Laplace transform of f of t, which is f of s divided by s. So, engineers, the Laplace transform of the integral from 0 to t f of tau differential of tau is equal to f of s over s, which confirms the suspicion, well, what our initial guess, that the Laplace transform of the derivative makes an f of s times s. Then the Laplace transform of the integral is f of s, but this time divided by s. Why? Because the integral is the opposite of the derivative. Therefore, on the s domain, instead of multiplying times s, you divide by s, right? And here on this formula, you don't have initial conditions. Now, what if you happen to have the Laplace transform of the second integral from 0 to t, from 0 to beta, f of tau, differential of tau, differential of, yes, the tau differential of beta, for example. Now this is second integral, so it has two integrals. So the result will be f of s divided by x squared, and that's it. Okay, just a comment. Now you can use this also as the Laplace inverse formula. How? The Laplace inverse of f of s divided by s is equal to the integral from 0 to t of f of tau differential of tau. Sometimes this formula is very useful when making the Laplace inverse. On the homework, I don't remember we have these cases, but just keep in mind that. Okay, so this is the Laplace transform of integrals. Now this is just just one step before the convolution theorem that we are going to see on the next video.